Welcome to our deep dive into the world of particle physics.
Hmm.
We got some listener questions about quarks and the Higgs boson and this thing called the Planck length.
Yeah, those are really interesting topics. And that kind of takes us from the tiniest building blocks of matter all the way to well, almost the edge of reality.
Yeah, exactly.
Yeah.
And that's what I thought was so cool, this idea that there's like a smallest possible size, a limit to how small things can get.
Yeah.
But before we go there, let's start with something I vaguely remember from high school quarks. So what are quarks and like why should we care about them?
Well, you can think of quarks like the fundamental ingredients of matter, you know? Like protons and neutrons are made of quarks, and those make up the nucleus of every atom
Right.
in your body. The planet, the stars, everything.
Okay.
And they come in different types, which physicists, being physicists, call flavors, up, down, charm, strange, top, bottom.
Flavor.
Yeah. And the way they combine determines, the properties of the particle that they create.
Okay, so I kind of get the flavors thing. But what makes quarks different from, say, like electrons? I always thought electrons were like the smallest things.
Oh, that's a great question. One of the key things is well, it's kind of a bizarre property called color charge. It's not actually color like we see it, but it's a way of describing how quarks interact with the strong force, one of the four fundamental forces of nature.
Okay, so it's like how electrically charged particles interact through electromagnetism.
Exactly. And the strong force is carried by particles called gluons. You can kind of think of them like these tiny couriers of the strong force zipping back and forth between quarks.
Okay, so now I'm starting to get a little lost. What does all this have to do with like the bigger picture? Why should I care about quarks and gluons?
Well, this is where it gets really interesting. You see, quarks are never found alone. They're always bound together in groups called hadrons. Protons and neutrons are the most famous examples.
Right.
But there are many others, each with its own unique properties and quirks.
So protons and neutrons are just the tip of the iceberg when it comes to hadrons.
Absolutely. And there's something really mind-blowing about the way these quarks are bound together. So most of the mass of a proton, for example,
Okay.
doesn't come from the mass of the quarks themselves.
Wait, what? If the quarks aren't that heavy, where does the mass come from?
It comes from the energy that binds those quarks together, the energy of the strong force itself. It's a bit like saying that the glue holding a brick together weighs more than the brick itself.
Wow.
Yeah, it's wild. It's a reminder that mass and energy are intimately connected, just like Einstein told us.
Okay, that's pretty wild. So we've got these quarks bound together by the strong force, creating all sorts of these exotic particles. But where does the Higgs boson fit into all of this?
That's a great segue. Remember how we were talking about mass? Well, the Higgs boson is the particle associated with the Higgs field,
Okay.
an invisible field that permeates all of space
Right.
and gives particles their mass.
Okay, I'm picturing like a giant cosmic swimming pool filled with this Higgs field, and particles are like swimming through it, and they get heavier or lighter depending on how they interact with it.
Yeah, that's actually a pretty good analogy. The stronger the interaction, the more massive the particle. It's kind of like trying to walk through honey. The thicker the honey, the harder it is to move.
So the Higgs boson is like the lifeguard of this cosmic swimming pool, making sure everyone has the right amount of resistance.
In a way, yeah. And the discovery of the Higgs boson back in 2012 at CERN, that was a huge moment for physics.
Right.
Because it confirmed a key part of the standard model, our best current description of the fundamental particles and forces.
So this Higgs field is everywhere. It's giving mass to everything. So that includes quarks too.
Absolutely. Quarks get their mass from the Higgs field just like any other particle. But here's the thing. The Higgs boson itself is surprisingly heavy, over 130 times heavier than a proton. Yeah. And yet it decays almost instantly. It's a real fleeting celebrity in the particle world.
That's fascinating. So we've got quarks. They're interacting with the strong force. They're getting mass from the Higgs field. I can't shake this feeling that we're missing something bigger.
Yeah.
Where does the Planck length fit into all this?
That's a great question, and it takes us to a whole new level of mind-blowing. Imagine, shrinking down smaller and smaller past the size of an atom, past even the tiny quarks themselves. We eventually reach a point where our understanding of physics breaks down.
Wait, so everything we've been talking about, quarks, the Higgs boson, all of that, it only works down to a certain point.
Exactly. And that point is the Planck length, an incredibly tiny distance, about 10 trillion times smaller than the width of a human hair.
Wow.
Yeah. At this scale, gravity and quantum mechanics, the two pillars of modern physics, they start to clash. It's like reaching the edge of a map and finding, "Here be dragons," scrawled across the unknown.
So the Planck length is like the ultimate frontier of physics,
Yeah.
where everything we know goes out the window.
In a way, yeah. And it raises some seriously mind-boggling questions. What happens to space and time at that scale? Could the Planck length be the smallest possible unit of space, like a pixel on a screen?
Right.
It challenges our very concept of what reality is made of.
Okay, I'm starting to see how the Planck length connects to everything we've been talking about. It's like this ultimate scale where the rules of the game might completely change.
Exactly. And while quarks and the Higgs boson are incredibly small, they're still enormous compared to the Planck length.
Right.
It's a reminder that even in the realm of the incredibly tiny, there are still vast scales and mysteries waiting to be explored.
This is blowing my mind. So what are some of the theories that physicists are working on to try to understand what's happening at the Planck length?
Yeah.
And could we ever actually see something that small?
Well, that's where things get even more interesting. Let's talk about string theory, loop, quantum gravity, and the challenges of peering into this incredibly small and incredibly strange realm.
Okay, so the Planck length is like this ultimate frontier in physics, right?
Mm.
Where the laws of physics as we know them, they might completely break down. So what are some of the theories that physicists are working with to try and wrap their heads around this?
Yeah, well, there are some truly mind-bending ideas out there. One of the leading contenders is string theory.
Okay.
And instead of thinking of particles as, tiny points, string theory proposes that the fundamental building blocks of the universe are actually tiny vibrating strings.
So it's like the universe is a giant cosmic guitar, and these strings are vibrating at different frequencies, and that's what creates different particles.
Yeah, it's a beautiful and elegant idea, isn't it? The way these strings vibrate determines the properties of the particles we observe, their mass, their charge, and so on.
But how does string theory help us understand the Planck length? I mean, we're talking about scales that are so unbelievably small.
That's where it gets really interesting. String theory suggests that those strings, they have a minimum length, and that minimum length could be related to the Planck length.
So even these tiny strings, they can't get smaller than the Planck length. Is it like the resolution of the universe or something?
It's a possibility. And it could mean that space-time itself isn't smooth and continuous like we typically imagine, but rather made up of these tiny vibrating stringy units.
So like a universe woven from these tiny strings.
Yeah.
Are there other theories out there?
Yeah. Another major contender is loop quantum gravity.
Okay.
And this theory approaches things from the perspective of gravity itself.
Right, gravity, the force that makes things fall down. What does that have to do with the Planck length?
Well, gravity is much more than just things falling down, right? It's what shapes the large-scale structure of the universe, galaxies, stars, black holes. And loop quantum gravity suggests that space-time itself is woven together from tiny loops of gravitational energy.
Woven together, like some kind of cosmic fabric.
Exactly. And just like in string theory, these loops, they have a minimum size,
Okay.
which again could be related to the Planck length.
So both string theory and loop quantum gravity, they suggest that there's this fundamental limit to how small things can get a limit set by the Planck length.
Yeah, that seems to be a common thread in these theories. And it has huge implications for our understanding of the very beginning of the universe, the Big Bang,
Right.
and also for incredibly dense objects like black holes.
Okay, I'm definitely seeing how the Planck length ties all these seemingly disparate ideas together. But are these theories just, mathematical constructs, or is there any way to actually test them? Can we ever actually see something as small as the Planck length?
That's the million-dollar question. Direct observation at the Planck scale is beyond our current technological capabilities.
Right.
But physicists are incredibly clever, right? And they've come up with some indirect ways we might be able to find evidence for these theories.
Like what? What kind of clues are we looking for?
Well, one idea is to search for tiny fluctuations in the cosmic microwave background radiation,
Okay.
which is the afterglow of the Big Bang. And if space-time really is granular at the Planck scale, it might have left a subtle imprint on this radiation, like fingerprints left over from the universe's birth.
So we're looking for these faint echoes of the Planck scale in the oldest light in the universe. Are there other clues that we're looking for?
Another approach is to study the behavior of particles at incredibly high energies like those produced in the Large Hadron Collider.
Right.
And we might see subtle deviations from our current understanding of physics that hint at the underlying quantum nature of gravity.
It sounds like we're trying to catch these fleeting glimpses of the Planck scale in the most extreme environments in the universe.
Exactly. And who knows, we might even find hints of extra dimensions or other completely unexpected phenomena.
It's amazing to think that this incredibly tiny length scale could hold the key to unlocking some of the biggest mysteries of the universe. But let's bring this back to the particles we were talking about earlier. You mentioned black holes and the Big Bang. How does the Planck length change our understanding of these cosmic giants?
Yeah, that's where things get even more mind-boggling. Let's start with the Big Bang.
So we were talking about the Big Bang, the very beginning of everything, and how the Planck length might be involved. What's the connection there?
Well, imagine the universe in its earliest moments, right? It was incredibly hot, dense, unimaginably small.
Yeah.
We're talking a size that's mind-bogglingly smaller than even an atom.
So smaller than the Planck length.
Yeah.
But we've been saying that that's the smallest possible size.
That's the crux of it. Our current physics, which works so well in describing the universe we see around us,
Right.
it completely breaks down at those extreme scales. We need a new theory, a theory of quantum gravity to describe what was happening in those first fractions of a second after the Big Bang.
So the Big Bang is like the ultimate stress test for physics.
Exactly. It's a realm where general relativity, which explains gravity and large-scale structures, and quantum mechanics, which governs the behavior of particles at the atomic level, they need to work together. And we're still trying to figure out how to reconcile these two fundamental theories.
So the Planck length is right at the heart of this problem.
Yeah.
What about black holes? They're incredibly dense, too. Does the Planck length come into play there as well?
Black holes are fascinating objects.
Yeah.
They're regions of space-time where gravity is so strong that nothing, not even light, can escape. And at the center of a black hole, according to our current understanding, lies a singularity.
A singularity. What exactly is that?
A singularity is a point of infinite density where all the matter in a black hole is compressed into an infinitely small space.
Infinite density. That seems kind of impossible, doesn't it?
It does. And that's why many physicists believe that the singularity predicted by general relativity is a sign that our theory is incomplete. At those extreme scales, quantum gravity likely takes over.
Right.
And some theories, like loop quantum gravity, suggest that space-time itself can't be squeezed infinitely small.
So instead of a singularity where everything collapses into a point of infinite density, something else might be happening.
Exactly. There might be some sort of exotic quantum state at the heart of a black hole, a state governed by the rules of quantum gravity. It's a mystery waiting to be solved.
It seems like the more we learn about the Planck length, the more questions it raises.
Mhm.
But it's exciting, isn't it? This tiny length scale is pushing us to rethink some of the most fundamental ideas in physics.
Absolutely. The Planck length is a reminder that there's still so much we don't know about the universe. It's a challenge to our creativity and our ingenuity to come up with new ways to understand it. And who knows what incredible discoveries await us as we continue to explore.
It's been an incredible journey. We've gone from the building blocks of atoms to the very edge of reality itself, exploring quarks, the Higgs boson, and this mind-bending Planck length.
Yeah, and we've seen how these seemingly disparate concepts are all connected by this fundamental length scale where our understanding of physics breaks down and new mysteries emerge.
Yeah. You know, if there's one thing I've learned from this deep dive, it's that the universe is far more strange and wonderful than we often give it credit for. And exploring these fundamental questions about the nature of reality, it's what makes science so fascinating.
I couldn't agree more. And who knows, maybe one day we'll unlock the secrets of the Planck length and rewrite our understanding of the universe once again.
Until then, the journey continues. Thanks for joining us on this deep dive into the world of particle physics. Keep those questions coming and keep exploring.